All right, so in today's video, we're going to talk about a simple problem where you have a stick of unit length 1, okay? And we drop the stick from a height and it breaks into two parts, okay? And this point of breaking, as you can see on the screen, is pretty random, right? So we want to figure out, let's say the stick breaks into two parts, what is the expected length of the smaller part? Okay, so let me just visually explain you. So you have the stick and let's say it breaks, let's say it breaks here, right? So this is the smaller part and this is the larger part. But this point of breaking is random, so it could also break, let's say here. So we want to, now this becomes a smaller part, right? So we want to figure out what's the expected length of the smaller part. Okay, now I would encourage you now to pause the video and try it yourself, okay? So I hope you got to the answer of this question. If you did, that's excellent. If you didn't, that's all right. Let's try to first look at the hint and then we'll take it from there. All right, so let's say, you assume this is the stick, left hand is at 0, right hand is at 1. And let's say we assume the first point at which it breaks is at a distance x from the left hand, okay? So naturally, if I say this is the part 1, then this becomes the part 2, okay? So I know that part 1 is of length x and part 2 is length is 1 minus x, all right? Because both of these parts have to add up to 1. All right, so now I have to figure out what's the expected length of the smaller parts, but I don't know the smaller part. So use the structure and try to see if you can come up with a way in which you can use expectation now. Okay, I hope now you were able to work this out, but if you didn't, that's okay. Let's first figure out what is the smaller part. Smaller part is minimum of x and 1 minus x, right? So that's fairly standard. Like whatever the x is, it can go from, and also important thing is where does the x go from? So x can basically go anywhere from 0, technically, to all the way to left 1. I mean, at the extreme ends, I would avoid saying the equality because, it's a stick and it's practically impossible to just split at the extreme ends. So I would say x lies between 0 to 1, right? Okay, so now we want to figure out what the smaller part is. And we've already seen that the smaller part definition is this, which is minimum of both these parts. So now let's try to apply expectation here, okay? So expectation of the smaller part is basically, it's minimum of x into 1 minus x, and I have to find expectation of this, okay? So if we want to figure out, let's say, expectation of a general variable x, then it's given by this formula. So what it does is basically it says, okay, whatever the value x takes on, multiply this with the probability density function at that given value and integrate it over the domain of this function x. I've represented here with this capital D that is representing, okay, whatever the domain value, whatever the values over which x is defined, I'm going to use those information and I'm going to compute this. I'm going to integrate this all over the entire domain. Okay. So now let's try to do this. So expectation of smaller part here now. Smaller part is integration of minimum of x and 1 minus x times the probability density function of x. Now this is tricky and this is important part as well. If you pay attention, I think it's fairly simple. We know that the point at which the stick breaks is random, right? As stated here. So what that tells you, if there's anything random, that means any point is equally likely within the possible ranges of x, right? And now x here, as we know, can be between 0 to 1, right? And we know that it's all random. So that basically tells us that x is uniformly distributed. X is actually independently and identically distributed over uniform distribution, right? Uniform distribution with values ranging from 0 to 1. You can exclude the extremes, right? So okay, so it's uniform distribution, extreme ends ignored, but it can be anywhere between the two. Okay, now we know, okay, probability density function of a uniform distribution is 1 over b minus a, where b and a are the extreme ends of this uniform distributions, right? So this becomes 1 over 1 minus 0, which is 1, right? So therefore, p of x is actually 1 here, right? And then you can multiply this with dx. And this can be simplified into, over the domain of x. And we know x has to lie between 0 to 1, so I can just directly say here. So it's minimum of x and 1 minus x over dx, okay? Now, if you look at this integral, it can be like, hey, this is this minimum function which is creating so much chaos here. I don't know how you integrate a minimum with two values in between, but it becomes fairly simple if you see how x and 1 minus x behave between 0 and 1, right? So if you look at 0, and let's say this is 1, x goes like this, right? So let's say this is x, right? This is x, and 1 minus x basically goes like this, right? This is again 1, okay? This is also 1 here. So if I say minimum, that what basically that means is, let me just quickly highlight this here. Minimum between the two here, what you will see is minimum basically says that at any given point in the domain or in the range of x. So now this is the domain here. This is domain of x, right? And this is range of x. Oh, this is basically the value, I would say. Not range, but yeah, it's value, let's say. Okay, so we know that between the domain of x, I have to find minimum between x and 1 minus x. So here, between 0 to 0.5, we know that 1 minus x is greater than, 1 minus x is greater than x for x less than 0.5. Okay, at x equals to 0.5, 1 minus x is equal to x, and at x greater than 0.5, we know that x is greater than 1 minus x, right? So if I have to find out the minimum, I can easily say that, okay, for point less than 0.5 here, I know that if I highlight here, x is smaller, and for x greater than 0.5, 1 minus x is smaller, right? So this is the minimum. So what we can do is we can split this integral into two, and we can easily solve this now. So now I think it should be fairly simple. So we do 0 to 0.5, we know that it's x dx plus integration of 0.5 to 1 is 1 minus x dx. Okay, and if you solve this, this is x squared by 2, 0. This is x squared by 2, apply the range, apply the limits, and this is x minus x squared by 2, apply the limits again, 0.5 and 1, so this becomes 0.5 squared by 2, 0 goes away, and this is 1 minus half, minus 0.5 plus 0.5 squared by 2, okay? So if you see this, this, and this cancels off, and this is 0.25, 0.25 by 2 times 2, so this is 0.25, which is 1 over 4. Okay, so I hope you got to this answer. It's a fairly simple puzzle, and but yeah, an interesting problem, right? If you had to solve this problem, let's say in 10 seconds, how would you do it? Now that's an interesting twist, right? So there is a way out there. So I'll let you now pause and think about what is a very simple way, intuitively, how you could have come to this answer. Okay, so I hope you got to the answer, but in case not, let's, in fact, this was something I also learned when I was speaking to one of the students, is let's say, we want to find out the expected value, okay, of the smaller part. Now, we don't know what the smaller part is, but we know that the smaller part has to be less than or equal to, at the very max, equal to 0.5, right? So the smaller part, and we also saw this, what I'm saying is it has to be less than or equal to 0.5, right? And we also saw this here. So this is highlighted, in this particular part here. This has to be less than or equal to 0.5, and this is 0.5 line, right? So it's always here. So now we know, okay, the smaller part is less than or equal to 0.5, but we also know that the breaking point is random, right? So we know that the length of the smaller part is also going to be randomly defined, right? Because the breaking point is breaking point is random, so wherever the split happens, that would decide the length of the smaller point. So naturally, the smaller point, the smaller part, is the length, the probability distribution of it is also going to be uniformly distributed because it's equally and identically distributed but uniform. Okay, so naturally, if I say that, okay, the length of the smaller part, and I'm just representing here, this is 0, this is 0.5. This is only smaller part length. Small part length. This is possibilities. We don't know, right? But let's say I say, it can be, let me represent this correctly. So we don't know the smaller part precise length, but we know it's uniformly distributed, right? Because it's random, it can break at any point. So this uniform distribution lies between 0 to 0.5. And if I tell you, okay, what's the expected value of this distribution? This is For uniform distribution, the expected value is always a plus b by 2, where a and b are the extreme ends of uniform distribution. So, okay, so if, let's say it starts from here and it ends here and it's uniform distributed, then the expected value is a plus b by 2. And if you do this here, it's 0 plus 0.5 by 2, which is 0.25, right? So you can also solve this intuitively if you got this. There's a little bit of intuition involved here, but if you want to be rigorous, I think the first approach is perfectly fine as well.